Today, at an international exoplanet conference, the team who built the high-accuracy radial velocity planet searcher, better known as HARPS, the spectrograph for ESO's 3.6-meter telescope, reports on the incredible discovery of more than 30 new exoplanets, cementing HARPS's position as the world's foremost exoplanet hunter. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host Dr. J, aka Dr. Joe Liske.
Hello and welcome to the ESOcast. In this episode, we have another major exoplanet discovery coming to you from ESO's La Silla Observatory. And we're not just talking about one exoplanet, we're talking about no less than 30. It's exoplanets galore!
Including these new results, data from HARPS have led to the discovery of more than 75 exoplanets in 30 different planetary systems. In particular, thanks to its amazing precision, the search for small planets, those with a mass of a few times that of the Earth, known as super-Earths and Neptune-like planets, has been given a dramatic boost. HARPS has facilitated the discovery of 24 of the 28 planets known with masses below 20 Earth masses. As with the previously detected super-Earths, most of the new low-mass candidates reside in multi-planet systems with up to 5 planets per system. In 1999, ESO launched a call for opportunities to build a high-resolution, extremely precise spectrograph for the ESO 3.6-meter telescope at La Silla, Chile. Michel Mayor from the Geneva Observatory led a consortium to build HARPS, which was installed in 2003, and was soon able to measure the back and forward motions of stars by detecting small changes in a star's radial velocity, as small as 3.5 kilometers per hour, or a steady walking pace. Such a precision is crucial for the discovery of exoplanets. The radial velocity method, which detects small changes in the radial velocity of a star as it wobbles slightly under the gentle gravitational pull from an unseen exoplanet, has been the most prolific method in the search for exoplanets.
In return for building the instrument, the HARPS consortium was awarded 100 observing nights per year over a 5-year period. Now, this time was used to carry out one of the most ambitious systematic searches for exoplanets so far implemented worldwide, by measuring the radial velocities of hundreds of stars that might harbor planetary systems.
The program soon proved very successful. Using HARPS, Mayor's team discovered, among others, the first super-Earth around Mu Ara, the trio of Neptunes around HD 69830, Gliese 581d, the first extrasolar planet in the habitable zone of a small star, and the lightest exoplanet ever detected around a normal star, Gliese 581e. More recently, they found a potentially lava-covered world, with density similar to that of the Earth's.
These observations have given astronomers great insight into the diversity of planetary systems, and they've helped us to understand how they might form.
The HARPS consortium was very careful in their selection of targets, with several sub-programs aimed at looking for planets around solar-like stars, low-mass dwarf stars, or stars with a lower metal content than the Sun. Although it was thought that giant planets couldn't form around low-mass stars, the HARPS team has found several of them. The number of exoplanets known around low-mass stars, so-called M-dwarfs, has also dramatically increased, including new super-Earth candidates.
Although the first phase of the observing program is now officially concluded, 2 new programs have been started. And the team still expects to make many new discoveries from the first 5 years of data. There is no doubt that HARPS will continue to lead the field of exoplanet discovery, and especially pushing towards the detection of Earth-type planets. This is Dr. J, signing off for the ESOcast. Join me again next time for another cosmic adventure.
Every night, all year round, the ESO Very Large Telescope, or VLT, opens its 4 giant eyes to scrutinize the beautiful southern skies. Each eye is a huge mirror, 8.2 meters in diameter, that gathers the light of the night sky and reflects it into optical systems that form ultra-sharp images of the universe. But keeping the VLT's eyes clear requires each mirror to be cleaned and recoated occasionally, a delicate and complex procedure. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host Dr. J, aka Dr. Joe Liske.
Hello and welcome to the ESOcast. In this episode, we're going to follow the recoating of one of the VLT's primary mirrors. Although this happens quite regularly, this is far from being a routine procedure. Under the open sky, dust collects on the surface of the mirror. And although this layer of dust is very thin, it nevertheless degrades the quality of the astronomical observations. And so, the mirror must be cleaned regularly. In fact, it must not only be cleaned, it must be recoated, meaning that its thin layer of reflective aluminium must be replaced. The ESO technicians and engineers must work both quickly and carefully to complete this operation on the fragile 17 cm thick mirror in order to limit the telescope's downtime.
First, the telescope must be prepared so that the mirror and its cell can be taken out. The team is removing an instrument attached to the mirror cell. Outside, a custom-built carriage is moved into position. This carriage will support the mirror and the cell, cushioning the load during transport. A dedicated platform lifts the carriage to the mirror deck. When it reaches the deck, the carriage slides into the building on a stream of pressurized air, ending up just below the mirror and the cell. The carriage is raised to receive the cell and mirror.
Once the cell is safely on the carriage, it can be disconnected from the rest of the telescope. All the bolts are released and the data and control cables are removed. Now this is always a pretty tense moment, and the team is working very carefully to make sure that they don't damage the fragile mirror. After all, there is no spare at ESO, and making a new one would take years.
The surface of the mirror is extremely vulnerable. It must be covered before it is taken out of the building. The cover not only protects the mirror, but also prevents it from concentrating sunlight and burning anything in its path. Before the mirror can be covered completely, a smaller mirror must be dismounted. This mirror sends the light gathered by the main mirror to different instruments at the telescope. During the coming days, the optical engineers will inspect and clean this mirror as well. Eventually, the larger mirror is completely covered. The carriage slowly slides out of the telescope building, supporting the full weight of the mirror and the cell, a substantial 50 tons. Once again, the lifting platform is used, carefully lowering the carriage to ground level. A truck brings in the hydraulic trailer. The trailer is carefully positioned to take the precious load. The load is secured with chains to prevent it from sliding off the trailer in case of an earthquake or a sudden stop.
The team is now ready to start the trip down the mountain to the recoating plant. This journey is a crucial stage in the whole process. Before the mirror is brought out, the weather must be checked thoroughly. High winds must be avoided at all costs during the transit, because any flapping of the lightweight mirror cover might scratch the mirror. Furthermore, the truck driver is supposed to never apply the brakes, because an abrupt halt might be dangerous for the mirror. And so the truck moves along at a leisurely 5 km an hour. But even at this walking pace, it eventually arrives safely at the mirror maintenance building.
The first task at the mirror maintenance building is to remove the mirror from the carriage and its cell. The carriage is positioned under a custom-made handling tool. Brackets connect the mirror and the cell. Engineers have to release each one manually. This may sound like a routine job, but with the sensitive mirror surface only centimeters away, it requires the team's undivided attention. Forgetting to take off even one bracket could damage the mirror severely during the lifting operation. The team is only ready to lift the mirror off its cell after a triple check of every bracket. Hooks are lowered to bear against the back of the mirror, and the handling tool lifts the mirror up and off the cell. Now the cell can be removed. Subsequently, the mirror is lowered again to allow some work to be carried out on its back surface. Before the optical engineers start work on recoating the optical side of the mirror, they must clean its back surface by hand. This cleaning is essential as it removes oils, particles, and other contaminants that could damage the mirror in the vacuum chamber. Afterwards, the bottom half of the vacuum chamber is brought in and the mirror is carefully lowered into it. The mirror is next taken into a clean room.
The first action in the clean room is to treat any badly polluted areas on the mirror manually. This requires a steady and skillful hand in order to avoid scratching the surface. The point of doing this is to remove any particles that might not be easily flushed away during the subsequent washing. Afterwards, the vessel holding the mirror is positioned in the washing chamber, where the old reflective coating of the mirror is washed off.
The washing process begins and a giant purpose-built sprayer arm rotates just above the surface of the mirror. Ultra-pure water and chemicals are used. Under the critical eye of the optical engineers, the machinery does a flawless job and the operation proceeds smoothly. In the next stage, acid is used to remove the old aluminium coating. The real amber color of the dish appears. The mirror is made of special ceramics that don't deform under temperature changes. Again, the mirror is rinsed intensively to provide as clean a surface as possible. Once done, all the liquid is pumped out and the mirror is ready for the vacuum chamber. The vacuum chamber lies next to the washing unit. The mirror is placed in the chamber immediately after cleaning to avoid contamination with new pollutants. The lower part of the vessel is lifted up and the chamber is closed. The air can now be pumped out to establish a nearly perfect vacuum necessary for recoating.
Once the vacuum is established, the recoating can begin. The optical engineers use an electrically stimulated plasma for a molecular cleaning of the optical surface of the rotating mirror. Then, individual particles of aluminium are deposited on the mirror in a process known as sputtering deposition. This takes about half an hour. Only 12 grams of aluminium are used to create the new coating for the roughly 50 square meters of the primary mirror, and so the coating is only about 18 nanometers thick. It's really not a lot, is it? Finally, the moment of truth has come. Will the quality of the new coating meet the high standards of the VLT?
Recoating a mirror is always a tricky business. If the mirror isn't thoroughly clean, or if the vacuum chamber is contaminated, then the coating will be flawed. Tension is high as the chamber opens and the mirror is brought out. A first visual inspection suggests that the recoating has succeeded. But what really matters is how reflective the mirror is, so the percentage of light the mirror reflects and scatters is measured. The result confirms a high reflectivity of the mirror, and the experts are fully satisfied.
The recoating was successful and the mirror is all shiny and new again. Our team is now ready to take the mirror back up the mountain and reinstall it at the telescope. The VLT will be back in full operation exactly on schedule to provide astronomers with a superb view of our universe once more. This is Dr. J, signing off for the ESOcast. Join me again next time for another cosmic adventure.
A new telescope for mapping the sky is starting work at ESO's Paranal Observatory in Chile and has just released its first images. It's called VISTA, or the Visible and Infrared Survey Telescope for Astronomy, and it's the largest and most powerful infrared survey telescope ever built. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the universe's ultimate frontier with our host, Dr. J, aka Dr. Joe Liske.
Hello and welcome to another episode of the ESOcast. Now, even for an observatory like ESO, it's a special occasion when a new telescope starts operations. VISTA is the first survey telescope at ESO's Paranal Observatory, and it's dedicated to mapping the sky at infrared wavelengths. It will chart the southern sky to much greater depth and with much greater sharpness than has ever been done before. The first images have just been released, and they clearly show that VISTA is working extremely well.
Interesting things found by VISTA will form targets for detailed study both by the neighbouring ESO telescopes, such as the 4 8-metre VLT unit telescopes, and by other observatories on Earth and in space. VISTA will find the rare needles in the cosmic haystack, and then the VLT can study these needles in great detail, so astronomers can try to understand what they are and what's going on in the universe.
Well, VISTA was conceived in the UK about 10 years ago, and a consortium got together to get it built, and it's now become an ESO telescope as part of the UK's contribution on joining ESO.
VISTA has a main mirror that is 4.1 meters across, which makes it the largest telescope in the world that is entirely dedicated to surveying the sky. The mirror is also the most highly curved of its size and quality ever made, and its construction was a major challenge. The telescope is housed in a dome near ESO's VLT on Cerro Paranal, which means that it shares the top quality observing conditions of that site.
At the heart of VISTA is a 3-ton camera containing 16 special detectors sensitive to infrared light with a combined total of 67 megapixels. This huge instrument provides the widest sky coverage of any astronomical near-infrared camera.
VISTA is a telescope with an infrared camera, and this allows us to look at the sky in a way that we can't see with an optical camera. So specifically, infrared cameras see preferentially cool objects, objects at a high redshift, or indeed objects that are hidden behind dust clouds.
VISTA is performing a total of 6 huge surveys over the next 5 years. Some focus on small patches of sky for long periods to detect extremely faint and distant objects, and others image the entire southern sky. The surveys study the distribution of galaxies and galaxy clusters, help unravel the mysterious nature of dark matter and dark energy, and look for rare objects, all the way from tiny but dangerous near-Earth asteroids out to the most remote quasars in the early universe. Our own Milky Way galaxy and its neighbours, the Magellanic Clouds, also received their own surveys.
VISTA generates several hundred gigabytes worth of data every night of observing. That's about as much as all of the VLT instruments put together. These data flow into ESO's archive system at its headquarters in Germany, and they are then sent on to the UK for further processing. The first images show the power of the telescope to image large areas of the sky quickly and deeply.
One of the first VISTA images released shows the Flame Nebula, a spectacular region of gas and dust where stars are being formed. VISTA's infrared eyes can see through the dust and reveal the cluster of hot young stars in the heart of the cloud. At the bottom of the wide VISTA field of view, the ghostly form of the Horsehead Nebula is faintly visible. VISTA has also created a dramatic view in the direction of the centre of our Milky Way galaxy. The wide field of view of the telescope and the highly sensitive infrared detectors of its camera allow over 1 million stars to be seen, many normally hidden behind dust. The Fornax cluster of galaxies is one of the nearest rich collections of galaxies. VISTA's large field allows many of the cluster's galaxies to be imaged at once, including the elegant classical barred spiral galaxy NGC 1365 at the lower right. This unique image shows several of VISTA's impressive capabilities.
Well, VISTA's users will be not only the European astronomers who set up and specified these surveys in the first place, but because they're public surveys and the results will be available worldwide, astronomers over the whole world will be using them to extract exciting results. And in many ways, history shows that the most exciting results that come out of things like this are often what you least expect. And obviously, I don't know what that is.
VISTA will give astronomers an entirely new view of the southern sky, and we're all eagerly awaiting the results from this powerful new addition to ESO's observational toolkit. This is Dr. J signing off for the ESOcast. Join us again next time for another cosmic adventure.
This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the universe's ultimate frontier with our host, Dr. J, aka Dr. Joe Liske.
Orion the Hunter is one of the most striking constellations in the sky, and is a familiar sight to amateur and professional astronomers alike. The Orion Nebula is faintly visible to the naked eye as a dim glow in the Hunter's sword. This swirling cloud of gas and dust is 1500 light-years from Earth and has fascinated astronomers since the earliest days of the telescope. Appearing to the eye as a small cluster of blue-white stars surrounded by a mysterious mist, the nebula's vast dusty regions have long hidden from human eyes an enormous stellar nursery full of young, hot stars. The Visible and Infrared Survey Telescope for Astronomy, or VISTA, has taken a spectacular new image that reveals some of the nebula's buried secrets. VISTA is the latest addition to ESO's Paranal Observatory in Chile, and it's the largest survey telescope in the world, with a mirror measuring 4.1 meters in diameter. It's dedicated to mapping the sky in the infrared part of the spectrum. By looking in the infrared instead of visible light, VISTA is able to peer straight through the obscuring gas and dust in the Orion Nebula. That's because in the infrared, at about twice the wavelength of visible light, the dust in the nebula turns largely transparent, giving us a clear view of the young stars that lie within. No other telescope has ever been able to not only see through the dust to reveal the hidden features buried within the Orion Nebula, but also to show its huge extent in amazing detail in a single image. At the very heart of the nebula lie the 4 brilliant stars forming the trapezium, a group of very hot young stars pumping out fierce ultraviolet radiation that is clearing the surrounding region and making the gas glow. Observing in the infrared also allows VISTA to reveal many other young stars in this central region that cannot be seen in visible light. In this dusty region of the nebula, gas jets shot out by young stars at around 700,000 kilometers an hour have collided with the surrounding gas and dust, exciting it and sculpting strange red shapes. Normally invisible, these curious wisps provide important clues for astronomers as they try to understand how stars are born and what happens in their early years. As impressive as this image is, it is just the beginning of what VISTA will reveal with its unparalleled ability to survey the sky, both quickly and deeply in the infrared part of the spectrum. This is Dr. J signing off for the ESOcast. Join me again next time for another cosmic adventure.
Imagine looking up at the night sky and seeing details on the surface of a star millions and millions of kilometers away. Imagine having eyesight so keen that you could check out the surroundings of a black hole. Using ESO's Very Large Telescope interferometer at Paranal, astronomers are now making these fantasies a reality. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host, Dr. J, aka Dr. Joe Liskett.
Hello and welcome to another episode of the ESOcast. This time, we'll take a closer look at a fascinating special observing technique that gets used at ESO's Very Large Telescope, or VLT for short. This technique is called interferometry. It lets you combine the light collected by two or even more telescopes in such a way as to make the individual telescopes act as if they were part of a single virtual telescope that is much bigger than the ones that you started with.
Each of the 4 VLT unit telescopes has a primary mirror with a diameter of 8.2 meters. Such big mirrors are necessary because they collect more light and provide sharper images. Under ideal conditions and with the appropriate technology, the individual VLT unit telescope can see details of objects in space that are equivalent to viewing a tennis ball on the International Space Station from the Earth. This corresponds to a distance of about 350 kilometers.
Now this may sound like a really impressive number, but astronomers figured out that they could do even better. Because frontline research requires studying the heavens in ever-increasing detail, new ways were sought to increase the VLT's already eagle-eyed vision even further.
And this is where interferometry comes in. Interferometry combines the light received by 2 or more telescopes that are simultaneously observing the same object. This allows astronomers to pick out details as sharply as if observing with a single telescope whose mirror has a diameter equivalent to the largest distance between the telescopes. The VLT design always had the use of interferometry very much in mind. The 4 8.2-meter unit telescopes of the VLT were built in a roughly trapezoidal configuration that can generate a virtual telescope mirror of up to 140 meters across. In addition, 4 movable 1.8-meter auxiliary telescopes can be combined in a configuration with an equivalent diameter of up to 200 meters. This gives images up to 25 times sharper than those from a single VLT unit telescope.
Combining the light collected by different telescopes is a major technical challenge, and it requires incredible precision. The light beams from each telescope have to pass underground through a complex system of mirrors and delay lines before they can be combined at the common focus.
Delay lines are an integral part of the VLT interferometer's complicated optical system. They ensure that the light beams arrive simultaneously at the common focus. To achieve this, several movable carriages loaded with ultra-smooth mirrors constantly adjust the light beams with extreme precision. The light paths must be kept equal to distances less than 1/1000th of a millimeter over a distance of 100 meters. Without this kind of accuracy, the light cannot be analyzed properly by the observatory's instruments.
The VLT interferometer really is a masterpiece of technology. In order for it to be functional every night, all of its many high-tech components must interact with flawless precision. Only then can astronomers benefit from the enormous observational power of this fantastic instrument.
The VLT interferometer provides astronomers with the ability to study celestial objects in unprecedented detail. It is possible to study the surfaces of distant stars, to determine the shape of asteroids, or even capture the surroundings of black holes. The VLT interferometer has produced one of the sharpest images ever obtained of a star. The breathtaking sharpness of this image is equivalent to seeing the head of a screw on the International Space Station from the ground.
These are really great examples of the superbly sharp vision that can be achieved with a VLT interferometer. In the future, this instrument will continue to be a valuable tool for astronomers studying the universe in unsurpassed detail. This is Dr. J, signing off for the ESOcast. Join me again next time for another cosmic adventure.